All right, today we have Gabi Zafrir tell us about non-invertible symmetries of n equals 4 super Young mills and twisted compactification. Take it away.
Okay, thank you very much for the introduction. So this talk today is going to be based on this paper. It was appeared recently on Archive and was done in collaboration with Justin Cady and Yunchin Zhang. Right, so the name suggests this talk is going to be concept about symmetries. A minute. Oh, okay. All right, so let's say this talk is going to concept about symmetries. And of course, we all know the importance of symmetries in physics, but recently there has actually been a renewed interest in this subject, which is actually prompted by the discovery, or perhaps I should say rediscovery, of various novel types of symmetries. It is then hoped that studying these novel types of symmetries, we will be able to learn us more about physics in general. One particular answer, for instance, is learn about dynamics of field theories, due to, let's say, the constraint that these symmetries can hold energy flows. In this talk, I'm going to concentrate on one specific type of these new types of symmetry we discovered that is not usually called non-invertible symmetries, particularly because of their appearance in a specific theory, which is the well-known four-dimensional n equal to 4 super Young mills theory. We'll also wish to apply this study, but we'll apply it actually to somewhat of a novel idea, that is, instead of trying to constrain known RG flows, we actually try to use these symmetries to generate new RG flows using the method of twisted compactification. We'll argue that you can use this to get new 3D n equal to 6 SCFTs. So that's the general idea. And the plan for this talk is going to be as follows. We'll begin with some introduction, mostly concepts about introducing this idea of non-invertible symmetries. We're then going to talk about non-invertible symmetries in the context of n equal to 4 super Young mills theory. Then we talk about the application of the twisted compactifications. And finally, I will end up with some conclusions. All right. So, of course, know that symmetries play a very important role in physics. You probably first encounter them in the context of Noether's theorem and the relation with conservation laws, which later on become more identities in quantum theories. Additionally, they also give us selection rules. In the concept of quantum field theory, they're also quite interesting to the constraint they lead on the normalization group, and not only to the Tooth anomalies. Now, recently, there has been actually a quite renewed interest in symmetries. This renewed interest comes from several observations. It was recently made or recently remade. The most notable of them is the relation between symmetries and topological operators. Now, the idea is that to every symmetry, you can associate a topological operator. And to illustrate it, it's convenient to take a specific example. Here we're going to take the example of a U1 global symmetry. So in that case, we have a conserved current. So we can have a one-form that obeys this relation. We can use it to define a conserved charge by integrating the time component of the current on some spatial slice. Particularly, we can exponentiate the charge and get an operator that is defined on that spatial slice. We can also more generally define it on some codimension 1 manifold M via this expression. What this operator basically does is basically implement the action of the symmetry on half of the space. So roughly, it's a codimensional partition of space to two parts, and roughly half the part is related to the other one by an action of the symmetry. As such, if you have a local operator, if that operator crosses the topological survey, it transfers up to the action of that symmetry. Now, interesting property of this operator is it's actually topological. This follows from the current conservation equation. If you change this surface by a little bit, the change can just integrate to 0 to this relation. And as such, this operator is invalid under small changes, at least as long as you don't cross any operator insertions. Of course, what I talked about here is, of course, on continuous symmetries because we need the current, but similar ideas also work for discrete symmetries, even though you don't have a conserved one. But you can still associate them with a topological operator that roughly partition of space into two parts, where the two parts being related by the action of the symmetry. All right, so various properties that we know of symmetries can then also be translated to properties of the associated topological operators. A particularly important example that we use later on is the group law property of symmetries. We know that if you have a symmetry, if you have two symmetries, then we can combine them together to form a new symmetry operation. In general, this is embodied by the fact that symmetries form a group. This is also can be characterized into property of topological operators, particularly property known as the fusion rule of topological operators. So say we have two symmetries, we can associate them two topological operators, one for each of the symmetries. So these are topological, they shouldn't matter. We can move them continuously on. In particular, we can move them so that they merge together. In that case, we expect the combination to be described by a different topological operator, And this is kind of process of fusion. You can take two topological operators, fuse them together, and generate a new one. In this case, for the specific for U1, this just mimics the general group law property of the U1. You have a transformation with one angle, another one, and you can combine to get something the sum of the angle. You usually write this fusion one like this. Okay, so you can now wonder what is this, all of these things help us, or why it's useful to consider it. The main reason why it is useful to consider this relation to topological operators, that this naturally allows various generalizations that are less apparent to just one-dimensional symmetries. In particular, there are two particular generalizations that have been explored recently in the literature, and they will be what we mainly want to talk about today. So we've seen that this general standard symmetry is topological of codimension 1. But one opportunity to generalize the topological of higher codimensions. This leads to what is known as a higher form symmetry. These symmetries then don't act on local operators, but rather act on extended operators. In particular, we usually use a notation of a p-form symmetry for a symmetry that acts on a p-dimensional object, and these are associated with topological operator of codimension p plus 1. One other generalization, in particular, is actually the main center of this talk, is that there are non-invertible symmetries. These are symmetries that actually do not form a group. But in particular, the symmetries that actually, their name comes from the fact that elements don't necessarily possess an inverse. The reason why these can usually fail to form a group is that they still, as I mentioned, they still have a fusion rule. You can still merge two of them to form a new topological operator. But the new operator you will get in general is not just one operator, but just some direct sum of operators. In particular, it's then possible to not be able to find, given some symmetry, you may not be able to find an inverse symmetry, I would call it a bar, so that the product of these two, the fusion of them will just be the identity. But in best, you can find the identity plus some additional element. This leads to them not possessing an inverse, and usually refer to non-invertible symmetries. Right? So there are actually at this point many known examples of non-invertible symmetries. No? Of course, initially it was mostly in 2 dimensions, but again, by now we actually have other examples also in about 2 dimensions. And there are various different ways we know to realize them. One way is you can gauge non-abelian discrete symmetries. In this case, you usually get a dual symmetry that's actually non-invertible. Another common way to do it is if you have a symmetry and another symmetry with a mixed anomaly, you can sometimes if you gauge one of the symmetries, the other one becomes a non-invertible symmetry. And another option that will actually be the main option we'll talk about today is that symmetry is under gauging. It's a specific case where your symmetry is an invariant under gauging a discrete symmetry. Now, I should say that this, of course, is a non-exhaustive list. There are various other ways of getting an invertible symmetry. And of course, it's also non-exhaustive references. That, at least in this year, and also in the previous year, many of the references that talked about non-invertible symmetry. And I will not be able to cite everything, but I try to see at least some representative set of references here. All right. So, as you can probably see from this slide, most of this application of non-invertible symmetry involves gauging in some way. But we can try to discuss a little bit about what gauge a symmetry.
Can I interrupt and ask a question before you proceed?
Yeah, sure, of course.
So, when you have an invertible symmetry, you can couple it to a background field which enjoys gauge symmetry. Is there an analog of this for non-invertible symmetry?
Well, I don't know. I would suspect that you should be able to do it.
I mean, you would expect that there is some sort of gauge symmetry because that's kind of dual to the conservation law. But at the same time, that would mean that you have a generalization of a gauge field which is not associated to a group. No.
Yeah, I mean, you can define gauging of non-invertible symmetries, like in the notion that I will talk about in here, but basically by summing over all the insertion of topological operators. Mm-hmm. You would suspect there is probably some way of maybe also defining it in terms of the background field. But I don't know how to do it. This is also the question of whether you can have anomalies under these symmetries, because anomalies are represented by some terms involved in the background fields. Again, I don't know, but it's an interesting question.
Yeah, thanks.
Are there any other questions? Right, so no other questions. So I was talking about gauging of symmetry. So it's convenient to again start with just the standard symmetry that we all know. When you gauge a symmetry, what you basically do is you basically perform a sum over all possible anomalies. In the case where this is a continuous symmetry, your sum also involves local infinitesimal anomalies, which are usually given by the field strength, so you have to integrate over the connection through that. In the case of discrete symmetries, you don't have these, so the only thing you're going to have is some anomalies over a cycle. So you should usually just use some discrete sum over these anomalies. Now you can also represent formally this issue of gauging symmetry in the language topological operators, which would then allow you to generalize it to more cases. And again, for discrete symmetry, this can be implemented by summing over all possible insertions of topological operator of the gauge symmetry on various cycles. The idea here is that if you wrap the topological on some cycle, this is equivalent to turn anomaly on the dual Poincare cycle. Because if you have an operator on the cycle, when you go around that cycle, you have to cross the topological operator at some point, and then you come back only after the action of the symmetry, which implement the anomaly, basically. Okay, so now you can also consider the following interesting question. Is it possible if you have a theory that is actually invariant under gauging discrete symmetry? That when you take the theory, you gauge a symmetry, and you end up with the exact same theory you started with. And naively, this idea seems like it's not going to work for the following reason. Let's consider the simpler case when we have some theory, it will have a discrete, I assume abelian, anomaly-free zero-form symmetry that we call H. We consider gauging this symmetry. After we gauge the symmetry, in general, we expect that this symmetry H will now not be a global symmetry in the theory because it's now a gauge symmetry. And so our theory will have a different global symmetry, and therefore it will be a different theory. However, one interesting observation is when you gauge discrete symmetries, you actually get a dual symmetry back, which in this case it will be a D-2 form symmetry. This comes about because you can consider domain walls interpolating between, again, vacuum with different spaces related by the action of the symmetry. You can then consider operating creating these domain walls. In general, when the symmetry is a global symmetry, these operators are not genuine. The genuine surface operators, in this case, would be D-2 surfaces, because they are depend on the choice of where the domain wall sits. But if they become a global, but then you gauge the symmetry, they actually become genuine operators. So you'll have an additional operator dimension D-2, and they are acted by D-2 form symmetries you can then introduce. In particular, for the special case of the dimensions, the symmetry that you get back is actually a zero-form symmetry. So in that case, if you gauge a zero-form symmetry, you get back another zero-form symmetry. You can entertain the possibility that maybe you have a theory, you gauge the zero-form symmetry, and you get back to exactly the same theory, with the zero-form symmetry you gauged being replaced by the dual zero-form symmetry. Now, before briefly discussing some example where this happens, I have some two comments that will be useful later on. One is that you can ask, so I said so much if you gauge a zero-form symmetry, you get a D-2 form symmetry. And then you can ask what happens if I try to gauge this D-2 form symmetry. In general, when you do it, you just go back to the original theory. So you can actually invert the gauging by gauging this the D-2 form symmetry you get. Another thing is that this will be useful later is that this actually works very similar also if you gauge the zero-form symmetry, but some higher form, but some P-form symmetry. But in this case, the dual symmetry you get is not D-2, but D-P-2 form symmetry. All right, so to discuss some example where this happens, probably the most well-known example where you have this phenomenon is a two-dimensional critical SYM model. I will actually won't discuss this model in detail because I won't actually need to, but I do want to discuss a few features of it, notably having to do with the symmetry. So most of my discussion is actually going to be about the symmetry that this model has. So for our purposes, we need to know that it actually have two symmetries. Well, two symmetries that are non-trivially. There is, of course, also the identity operator. The identity symmetry does nothing. And these two symmetries can be represented by two topological operators. Now, we'll mostly use this notion of symmetry and topological operator interchangeably here. So one is the symmetry we call eta. It's just a Z2 zero-form symmetry. You can associate a topological operator that again cut your space to two, which one half related to the other one by the action of the Z2 zero-form symmetry. For those familiar with the SYM model, we see that it's implemented by the spin flip operation. The other one that is more interesting for our purpose is the symmetry called K, which basically is a symmetry under gauging the Z2 zero-form symmetry. We can again associate with a topological operator to it, that will again call K, which basically again partition our space into two parts, where the symmetry is not gauging one part, but is gauging the other part. So you can go into some half-space gauging of the Z2 zero-form symmetry. In the context of the SYM model, this is usually referred to as the Kramers-Barnier duality distance. Now, in particular, they obey the following fusion rules. Now here, this fusion rule just tells you that eta is a Z2 symmetry. If you fuse it, it will set it as the vector identity. These fusion rules actually tell you that K implements gauging by eta. Because it roughly means that if you perform the operation K, and you perform the symmetry operation eta and K, you get with the exact same thing. This is what will happen if you gauge the symmetry, because after you gauge the symmetry, you no longer distinguish operators that are different by the action of eta. The last fusion rule is the most interesting for our purpose because it tells you that K is an non-invertible operator. In particular, there is no operator, but if you put product by T, you just get the identity. The best you can do is get identity plus this additional insertion operator. This fusion is actually quite common when you have symmetries that come from gauging, which are, as I will now explain. So to understand this fusion, it's convenient to consider a two-dimensional theory on a torus. So I'm going to this will represent a torus. So this edge is interfaced with this edge and this edge with this edge. Let's consider introducing these two non-invertible defects, one here, another one here. So these defects basically involve a gauging of the Z2 zero form symmetry. So if you have a Z2 zero form symmetry here it will become gauged as we cross. Okay, and once we cross the other time we are gauging the dual Z2 zero form symmetry. So basically ungauging the Z2 original zero form symmetry, so it will be ungauged here. So basically in this region between the two, there's a blue region between these two K operators, the Z2 symmetry is gauged, and therefore we need to perform a sum of holonomies of the Z2 symmetry.
Gabi,
Yes.
This is an SU2 level 1 or level 2 affine algebra?
You're asking the critical Ising model?
Yeah.
I'm not sure if it has a representation as another. And again, I'm not actually going to need the details of the critical Ising model. It will mostly important here the behavior of the symmetries themselves.
I see. So, okay, so you will not use this language of affine.
No, I'm just into this. The thing is that I'm not actually going to need it. The only reason I'm saying is it's a bit easier to discuss this example in two-dimension, and a lot of the properties, not with the fusion, will are behaving very similarly also in the higher dimensional cases.
Mm-hmm. I see. Okay. Okay. Thank you.
No? Any other questions? All right. So as I was starting to say, you have these two operators, okay? Between these two operators, the Z2 symmetry is gauged, and as such, you are going to need to perform a sum of holonomies of the Z2 symmetry in this region. Now we can consider shrinking this region, basically bringing these two operators so that they coalesce on the same codimension one surface. In that case, we are now basically not gauging the symmetry in almost everywhere in space, except at one point, and that is precisely on this codimension one surface where the two operators rest. Here we still need to gauge the symmetry, and as I mentioned, when we gauge the symmetry, we need to insert the sum of holonomies, which initiates a trivial holonomy implemented by putting basically the identity element on the circle, or the non-trivial holonomy, that is the Z2 symmetry implemented by wrapping eta on the circle. Such when we merge the two operators together, we will not end up with the identity, but rather end up with the identity plus eta. This is the general property of symmetries under gauging. They will usually not be invertible because when you merge them together, you end up with some sum of holonomies instead of the identity. And as I said again, I'm not actually going into the details of this model, but these properties that I mentioned here are actually common in all the other models that involve gauging in some way or another. All right, so you see that in two dimensions, we can have invariance under gauging of discrete zero form symmetry, where here we again lose the zero form symmetry gauge, but we gain a new discrete zero form symmetry from the dual symmetry in such a way it's possible that the model after we gauge the symmetry is exactly equivalent to the model before we gauge the symmetry. Particularly, these symmetries under gauging lead to non-invertible symmetries, as in general, when you fuse them together, you end up with the sum of holonomies rather than just identity. However, this seems to be quite special to 2D, as once we go behind to a dimension higher than 2, then when we gauge the zero form symmetry, we don't expect to in general get a new zero form symmetry. And such it seems that this idea is not going to work behind the 2D. However, it turns out that you can actually do this, can still get non-invertible symmetry behind 2 dimensions if you gauge higher form symmetry. Specifically in 4 dimensions, if you gauge a 1 form symmetry, you actually gain a new 1 form symmetry instead. And as such, we can entertain the possibility that perhaps in 4 dimensions, it actually self-duality is under gauging a discrete 1 form symmetry. Well, again, you will gauge the 1 form symmetry, but you will then get the new 1 form symmetry in multi-spectral theory after gauging that will be equivalent to the original theory. Recently, many examples of these types have been discovered. Now we'll actually consider a specific example of where this happened, which is basically one of the purpose of the article, and that is the case of n equal to 4 superangles. Right, so that's what we're going to discuss next. But before that, are there any questions about what I talked about so far? Okay, so if there are no questions, let's continue. So we're going to consider n equal to 4 superiomials, and I assume you're all familiar with. N equal to 4 superiomial is defined by choice, at least the local part is defined by choice of gauge algebra. In our case, for simplicity, I'm going to consider the case where the gauge algebra is SU2. Although most of our cases can be generalized to the other cases. Now, even after you fix the gauge algebra, that is, you fix the local spectrum, you still haven't fixed the theory completely. You still have a choice of the precise, the non-local spectrum, not only the line operator spectrum, which then is given by choice of the precise group. There turn out to be 3 possible choices in this case. They correspond to the fact there are 3 possible non-trivial line operators you can actually choose to add to your theory. Specifically, since we have our gauge algebra is SU2, our local operators all form representation in the adjoint representation. So you actually have word lines in the adjoint representation. So you want to include these. Additionally, you can also include 2 lines in all representations consistent with every representation of SU2. These are kind of like the basic line operators to start with. Then you have some choice of line operators you want to add to them. Particularly since you don't have matter in the fundamental representation, you don't necessarily have Wilson line in the fundamental representation, but you can choose to add them. So this is one option you can add, Wilson line in the fundamental representation. Additionally, you can choose to add 2 lines that are consistent with all the adjoint representation or product of the adjoint representation, but not considered with the fundamental representation. This is what I call a fundamental 2 line. It is also possible to consider some line that carries both magnetic charge in the fundamental, like the fundamental 2 line, and electric charge like the fundamental Wilson line. So I call a fundamental dionic line. So you have these 3 options. They're actually mutually exclusive because they don't obey their quantization with one another. So you can only choose to add one of them. This leads to 3 different global variants of the theory. One called SU2, where you add the fundamental Wilson line, but then don't add the other one. And another one called, and 2 other ones called SU3 plus and SU3 minus, where in SU3 plus you add this fundamental 2 line, and SU3 minus you add the fundamental dionic line. All of these theories also have a Z2 form symmetry that basically act on this corresponding line that you've added. One other important thing to know is to actually move between the different global structure by gauging the Z2 form symmetry. For instance, if you gauge the Z2 form symmetry of this SU2 theory, you transfer to the SU3 plus theory. This comes up because now the fundamental Wilson line is no longer gauging values, it's projected out of the spectrum. And that you can now start adding one of the lines that were not consistent with it, particularly the fundamental 2 line, and get to the SO3 plus theory. As I said previously, you do that, you lose the Z2 form symmetry, but you get a new Z2 form symmetry that now acts on this fundamental 2 line.
Gabi?
Yes.
What's the origin of those names?
Oh, the origin of this, you mean the SU2, SO3, SO3 plus 2 minus?
Yeah.
All right, this is basically taken from this paper, which already introduced this concept. The logic is this one. In SU2, naturally you have a fundamental representation, so you want to add the fundamental Wilson line. Alternatively, in the SO3 variants, you don't have any fundamental representation, so you will want to add all magnetic charges consistent with it. So you want to add the fundamental 2 line. You have 2 choices of whether or not you want to add them. One of them, again, is whether or not they carry electric charges or not carry electric charges, and then you just distinguish them in plus and minus. I don't have any really good reason why you just choose this one, but that's the choice that they made.
So plus refers to existence of electric and then absence of electric?
Actually, it's the opposite way. Plus refers to the fact that your fundamental 2 line does not carry electric charge, while minus refers to the fact that it does carry electric charge.
I see. I see. Okay, yeah. So it's another poor choice of names?
I don't know. That depends, I guess, on your position. Okay, but I can see why you are a bit, you find it a bit strange.
Yeah, I see. Okay. Thank you.
No problem. Other questions? All right. So, another important property of n equal to 4 if you are going to use is the property of S duality. Notably, if you have n equal to 4, you can relate if you have two n equal to 4 theories that are S2 basically relates to 2 different n equal to 4 theories that actually secretly describe the exact same physics. Notably, if you have 2 theories, let's say with some coupling constant tau and mills, then any 2 theories related by the summation to the transformation, which in general can be generated by 2 elements, S and T, that acts on this coupling constant in this one. So 2 theories related by this transformation actually secretly describe the exact same physics. Even though they might look differently, Notably, they will have different topping constants. One other interesting aspect of S duality is that it actually also changes the global structure. So in general theory, while the local structure remains the same, theories related by this transformation in general also have different global structure. It is in particular, in our case, the variation between SU2 and SU3 plus T1 actually changes, and it's summarized in this table, or exactly in this diagram, basically, how the different global structure changes. Now, let's consider looking at a very special case. We take our global structure to SU3 minus, we will fix tau n to be equal to I. Now, the special thing about this choice is that the theory actually becomes invariant under the S transformation. Notably, if you look at the S element of the SU2Z duality, it takes this transformation, so tau equal to I is actually fixed at tau n mills, and also it actually this particular choice fixes the global structure. So in this theory, this transformation is a non-trivial mapping of your local of all of the degrees of freedom in such a way that you end up with the exact same theory, that it is actually a symmetry. So this specific theory actually possesses a symmetry, which is also with this S transformation. Now you can ask what happened with this. What if we now take the other global variance, SU2 and SU3 plus, and tau n is equal to 1. Naively, we expect this thing to be related with SU3 minus theory by some gauging of the Z2 one form symmetry, which we would have expected would not do anything with the local operator. So we come up with naively would expect that some symmetry should be remain also in this theory. However, as you can note from this diagram, they are not actually invariant under S. So the interesting question is whether you can actually find a similar symmetry in this theory. And the answer is that you can find the symmetry, but you need to combine this S operation with another operation, specifically with gauging the one form symmetry. Now, to illustrate this, we're going to consider two interfaces between theories that I will going to call them sigma and S. Sigma is an interface where basically when you cross it, you're gauging the Z2 one form symmetry. So the two sides of the is basically a codimension one interface where the two sides are related by gauging the one form symmetry. Similarly, S is another interface where the two sides are related by the S duality transformation, even simply by the S transformation. Now let's consider the case when you have an SU2 theory with some value of dynamics at some point, at some part of an after space. Now, if we have an after space, once we cross sigma, we're basically related by gauging the one form symmetry, which changes SU2 to SO3 plus. So in this case, we now have SO3 plus with the same value of dynamics since gauging the one form, so it doesn't change dynamics. Now, once we cross the S interface, we're now again transforming an S duality, that changes SO3 plus back to SU2, but also changes dynamics. In particular, we can now combine the two interfaces and form one other interface that I will call N, where on both sides we have an SU2, but with different values of tau n mills. Now, if we fix tau n mills equal to 1, we now have the exact same theories on two sides. So this becomes from an interface, basically a symmetry operator, and it actually becomes a topological operator implementing a symmetry, which is actually the symmetry we discussed. It relates basically the S duality symmetry, but now the SU2 theory. So we can actually get a symmetry if we combine this by gauging the Z2 one form symmetry. However, there is a price that we have to pay for it, and that is that this symmetry now becomes uninvertible. The logic is exactly the same as before, and it comes about from the fact that we are now also involving gauging of a Z2 discrete symmetry. Simply, we can consider again having our space and inserting two of these N operators. So in between these operators, the Z2 one form symmetry is gauged. It's not gauged here, it's not really outside of it, but it is gauged inside in this region between. And as such, in this region, we're going to have to sum over elements of the one form symmetry. And again, once we merge these two operators together to form N squared, we are not completely eliminating. Gauging still remains localized on this codimension one defect. So N squared actually doesn't square to the empty, but actually square to a sum over insertion of the one form symmetry over various two cycles in the circle. Here I'm using this notation L sigma for where L is the topological operator of Z2 one form symmetry, wrapping some two cycle sigma, which in this case is located on this codimension one surface. Right, so what we have actually seen here that we started with some invertible symmetry given by S duality in the SO3 minus theory tau equal n is equal to 1, and you can actually which actually becomes an uninvertible symmetry in the other global variants, normally SU2 and SO3 plus. Now you can also ask, this is of course one representative example, because it is possible to find other such symmetries. Can you actually catalog them or try to do some classification of what sort of symmetries you can have in this class of models of this type? And particularly interestingly, is it possible to find non-invertible symmetries that are not related to an invertible one? Here, these symmetries can be thought of as some cousin of an invertible symmetry of the SO3 minus theorem. But it might be that there are some other symmetries that are actually not what we call intrinsic and invertible. They cannot be related to some invertible symmetry of a different global structure. So we have seen that we can understand these symmetries by an action of two operations. One is an SL2Z transformation, and the other one is gauging the Z2-1 symmetry. So now to try to classify these symmetries, what I will next try and understand, we can do this by basically first analyzing how n equal to the global structure of n equal to 4 transform under this combined operation of both the SL2Z transformations and this gauging of the one symmetry. So that's what I'm going to discuss next. But before that, are there any questions? Okay, so there are no questions. Continue. All right. So we can consider two families of operations that you can do. Here I'm going to again still remain processed on an SU2 n equal to 4 superangles. The most of us I can say can be generalized to other types of groups, even though some of the detail is going to change. So for the case of SU2, we're going to have two families of operations. One are again the S2 transformations. Which are defined as previously, we can expand them by two operations, notably the S transformation and T transformation. They operate on triangles in the following way. They form an SL2Z transformation. In this specific case of SL2, you can actually take it to be PSL2Z. And then the defining relations are this. In the more general cases, you will need to have a -1 instead of 1, but again, for SU2, you can just take it to be 1. Additionally, we're also going to define two additional operations. So I'm going to go to the sigma and tau operation. The sigma operation we've already encountered previously. This is just defined by gauging the Z2-1 function. But now we're also going to add another operation. We're going to go tau, which basically, it starts the theory with some invertible phase given. And this expression, here B is the background gauge field for the one-form symmetry, and PB is basically what does the Pontryagin square of B. For the purpose of this lecture, you can just think of it as B by B. But for various technical reasons, it's time to call the definition in terms of this Pontryagin square. So basically what this thing does, it just adds some counter term in the background gauge field for the one-form symmetry to your action. Normally, of course, since the counter term only involved in the background gauge field, it doesn't actually change the physics. But once we start gauging that symmetry, it will be important, which is why we'll consider it, and I want to consider adding it, and why you need to add it. Now, in general, these two transformations actually form an SL2Z, in this case, SL2Z2 action. So they can be given by these following defining relations. So next, we want to ask what happens to the various global structures of the SU2. Once you do all of this combined transformation, we can actually summarize all of these things in this diagram here. Now, note that since we are going to distinguish theories different by this invertible phase, we really need to, each one of the global values is now going to be split into two. One of them that has the invertible phase, and one of them doesn't have. If it doesn't have the invertible phase, it usually denotes by the subscript 0, and when it does have it, it is denoted by the subscript 1. These, of course, are transferred to one another by the action of tau, as you can see here. So the first thing we want to do is want to determine the orbit under DST sigma and tau transformation, as I mentioned, is summarized here. Now, there are various, the way you can do that is, first of all, some elements just know how they act, like tau, as I mentioned, transfer between, by adding or removing the invertible phase. Additionally, you also have various restrictions on the symmetries. Notably, you know they obey this relation, and they also need to commute with one another. In general, once you know some of these transformations, you can use this relation to fully fix the other thing. Additionally, you also know that if you don't distinguish theory different by the invertible phase, you should just get back to the SNT transformation I've shown before. You can also actually derive this more explicitly by using the partition function. Basically, if you assume some of these relations, you can use the partition function, you know these two relate to one another to derive the other ones. We illustrate this also in the paper, but I will not, for simplicity, I will not consider this here. Okay, so once you understand this diagram, you can actually use this to understand the general non-invertible symmetries you can have, or invertible one you can have, and in this model given by some symmetries under SL2Z transformations. So the idea is, for simplicity, I'm going to limit tau and Mill to the fundamental domain. The fundamental domain is the part of the aftermath plane where you can basically map any other points into it by some SL2Z transformation. So it's pretty convenient to do it. You can basically use SL2Z freedom to map everything back into the fundamental domain. And what's convenient in that case is that it makes the analysis more simple in the following way. So the first thing we need to consider when we want the symmetries, we want it to act trivially on the local operator spectrum, which in this case we need to find some subgroup of the SLT transformation that map time means back to itself. And in the fundamental domain, there turn out to be only two possible interesting cases where this happens, or in this case where time means is not zero. One of them is the time means equal to 1, which basically is not back to itself under the S transformation. The other one is time means limited to default, some cubic root of unity, which is basically given by the TS transformation. Now, this thing generally will give you naively an order 2 symmetry, and this will give you an order 3 symmetry, again, if they're invertible. I should know the theorem again, especially into SU2. In general, if you're in theories where in other theories, it's usually actually Z4 and Z6. What's the -1 element takes them trivially. However, so this thing will naively give you a symmetry as far as the local operator spectrum is concerned, but in general, they're not going to keep the line operator spectrum invariant. Notably, if you, for example, if you can look at the SU2 case, if you do the S transformation, you will not come back to SU2, but rather come back to SU3 plus, as you know previously. Now we need to find some combination of the sigma and tau transformation, so that if we get back to the original theory, instead of the combined action actually will become a symmetry. So in this case, we can note that if we do the sigma action, this will send us back from SU3 plus to SU2, and so S and sigma together should form a symmetry at tau young is equal to 1. Which in this case be non-invertible because it involves the sigma operation. Similarly, you can consider the S transformation. So you start with SU2, you do T, you get to SU2 1, and then if you do S, you end up with SU3 plus 1. So again, this S transformation, even though it acts as a symmetry on the local operator spectrum, it doesn't have the line operator spectrum back to itself. But now you can combine it with the tau and sigma action, and you return back to SU2. So in this way, you can read off the possible symmetries you have in this model, and you can summarize them in this table here. So you have two options, again, either a tau is equal to I, or a tau is cubic root of unity. You can have some choice of theory, basically one of the global variants and choice of invertible phase. And for each one of them, you can write the defect. What you have is given up in all of these cases, they involve one S element, and here they involve one TS element, because it's what requires to keep the local map tau is back to itself. But then they will differ by various applications of sigma and tau necessary to map the line operator spectrum back to itself. We can also note what we call the anality of the transformation. This is kind of like the analog of order of transformation for non-invertible symmetry. Since the symmetry is non-invertible, they don't really have an order in the usual sense. But you can still think of the number of times you need to fuse this operator with itself to come back to a sum of invertible transformations, which is what we call the anality. In particularly, for this choice of SO3 minus, the anality is 1, which basically just tells this operator is actually completely invertible. As we noted previously, since it doesn't involve any sigma insertion. This operator however is non-invertible and has anality 2, because n square actually corresponds to a sum of invertible transformation. Here just one from symmetry transformations. Now here these two operators have anality 3, so they are in particular you can note both of them are non-invertible. So one interesting aspect in these symmetries, as happened at this concept for SU2, that unlike in this case, there is actually no variant of the theory where this symmetry becomes invertible. This is some example of an non-invertible transformation that does not appear to be related to an invertible transformation in some way. Right, so I talked about how do this exercise for SU2, and you can in principle also do this exercise for other cases, although it becomes much more complicated. So this is indeed something that we did in the paper. We did basically for every possible choice of the gauge group, including exceptional groups. Of course, now the results in general become, and the idea in general is the same one. You first understand the action of the sigma tau and ST transformation, which you can summarize in diagram. The diagram becomes much more complicated. Here, for instance, I've just shown the sigma tau diagram for specific case of SO4 and S2. There is also a similar diagram with an SNT transformation if you want to look at it in the article. Then once you have the diagram, you can derive the symmetries, you do the SNT transformation required to keep the local spectrum, and then you read off what segment tau transformation you do, and you can summarize them you can then summarize them in a table, which again, you are shown an example of the symmetries that we have in this case for SO4 and S2. And similarly, you can do this to the other cases. And this leads to some central catalogization of the possible non-invertible symmetries, and also invertible one, you can have in n equal to 4 supernovae associated with symmetries under SL2 transformations. So that's one part of what we did. And in the remaining time of my lecture, I want to talk about the second part, and an application of these ideas, what you can use these symmetries to do. Particularly, we try to use them to generate new n equal to 6 SCFTs in 3 dimensions. But before that, are there any questions about what I've talked about so far? Right, so if there are no questions, move on. So the general idea is as follows. If you're given a symmetry, you can obviously consider inserting some holonomy on that symmetry around some given cycle. We're particularly interested to consider this in the context of circle reduction when we refer to the notion of twisted compactification. The idea is as follows. We can consider our theory on some d-dimensional flat space. We will take one space and turn it to the compact direction. So we basically consider our theory instead of RD minus 1 times S1. We expect that if we take the limit of the S1 swing to 0, we get some theory, some lower dimensional theory just on the RD minus 1. When we do this in general, we're going to enforce some periodicity condition around the S1. Usually we just take periodic condition, that is when you go on the circle, just go back to yourself. But if you have a symmetry, consider what is known as a twisted boundary condition or split periodicity condition, where your operator, when you go on the circle, doesn't come back to itself, but come back to itself plus the action up to the action of the symmetry. So this is something that you can consider this standard zero form symmetry. And as I mentioned in the previous of the spirit of what I mentioned in introduction, if you can do something in the usual form of the zero form symmetry, you should be able to represent it somewhere in the language of topological operators. In this case, you can represent it in topological operator, basically inserting the topological operator localized on some point on the circle. So this is a zero form symmetry. The sort of topological operator is a codimension 1 operator. You can insert it to fill this RD minus 1 space, and it's localized on some point on the S1. This basically mimics this. This basically enforces periodicity condition because if you can try to form this by basically taking the operator and moving it around the circle. When you come back, you have to, during this process, you will have to cross this insertion of this topological operator, and this is called N. So when you come back, you don't come back to yourself, but come back up to the action of this symmetry element. Right? So once you can phrase it in the language of topological operator, we then expect it to perform it to other types of symmetries besides the standard zero form symmetries. In particular, you expect to perform it also with non-invertible symmetry. Now, I should say that here I'm going to specialize to this very special case where you just do a circle reduction. So your compact space is just a circle. Now, the problem is that if you consider more complicated manifolds, particularly one that has some non-trivial or multiple group relations, then we know that the spectrum of this even of standard symmetries is limited by the multiple group relations. And this should presumably also may limit the ability to do twist computation even with non-invertible symmetries. But for the purpose of this talk, I'm going to ignore it and just look at a very simple case with just one circle. Now, this of course will be quite interesting to analyze and see what sort of theories you can get if you use twist computation with non-invertible symmetries. Notably, can you get theories that you would not be able to get otherwise just using standard symmetry. However, this of course you can do in any case you have a non-invertible symmetry. Unfortunately, analyzing compactification of Stalin Tarkin theories is in general difficult. Now, one place when we do know how to do this, or at least know how to make progress, is if we have enough supersymmetry. In that case, we can use various methods to do it. In particular, the case of n equal to 4, so permit and make a very nice case study because you have a lot of supersymmetry. So here you might be able to actually tackle this problem. Of course, this is only going to really help you if you are preserving some supersymmetry in the process of multiplication. But to really make progress, we first need to ask how many supersymmetry can actually preserve if we do some twist compactification by this symmetry that I represented here, which are some symmetries under SL2Z transformations. So how can we do that? As I mentioned previously, our symmetries are ultimately built out of 4 basic operations we mentioned, and these are the SNT transformation and the sigma and tau actions. So to understand how much supersymmetry we preserve, we only need to know how the supersymmetry transform under all of these 4 basic operations. So it's convenient to first start with sigma and tau. Since these always involve the one form symmetry in one way or another, they will actually only act non-trivial on extended operators, notably line operators. And as the superchargers are local operators, they should act trivial on them. So in this case, they should actually preserve the supercharger. However, this is not the case for the SNT transformation, which are actually known to have a non-trivial action on the superchargers. Particularly if you consider some general SL2Z transformation, so the time and limit transform in the following way, then your supercharger, your 4 superchargers collectively transform in this way, where this angle is given by the argument of the angle of the denominator. This in general is going to be non-trivial, And such, the symmetry that we have built, whether invertible or non-invertible, are not going to preserve any supersymmetry, since all the supercharges are going to transform trivially under them. However, at least those of you familiar with the S-fold will know, it is still possible to actually combine, to actually make a symmetry out of this that actually do preserve some supersymmetry by combining the action with an additional action of the R symmetry. Specifically, n equal to 4 superangles as an SU4R symmetry that acts on the supercharges, the 4 supercharges transform into the fundamental representation of the SU4. We consider combining the action of this symmetry that we previously mentioned, whether invertible or non-invertible, with an action of an element of the SU4R symmetry. They will particularly take to be a diagonal element, so it will look like this. The entries are all going to be phases. They will be restricted by this condition because it's an SU4. In this case, when you do the combined action of both the SL2Z transformation and this action, the supercharge transform in this following way. And now it's actually possible to make some of them invariant under the action if you make some clever of this sigma, of this phi angle. The maximum you can preserve is to preserve 3 out of the 4 Q's, which is actually given by this choice. This actually preserves 3/4 of the supersymmetry, it should actually preserve 12 supercharges. Now, I should note that these phases are going to ultimately end up to be some discrete ZK type phases, with K being related to the type of basically the order of the symmetry if it's invertible, or what I call the analysis in the non-invertible case. So practically what you're combining here with the symmetry that I mentioned previously is some ZK subgroup of the SU4R symmetry. And for more purposes, K will either be 3, 4, or 6. All right, so since you can actually preserve the supercharges, we expect to get some 3-dimensional 2 with n equal to 6 supersymmetry, which we presumably expect to be a 3D n equal to 6 SCFT. We'll next want to try to understand a bit more details about this 3D n equal to 6 SCFT. And one thing you can actually learn is we can actually get some understanding about the model space of that theory should be. Now, specifically, supersymmetric theory generally possesses a model space of Varchois. So in the case of n equal to 4 superangles, this model space of Varchois is given by various dev to the 6 edge on scalar fields. Now, I'm not going to discuss the structure of this model space in detail. First, because I don't have that much time. And second, because I'm pretty sure most of you already are familiar with it. I will say briefly that you can schematically think of it as being given by in span by various by the collection of gauge invariant operator. You can actually think in this form some trace of some power of the basic 6 edge on scalar fields. Now, the number of such operators is given by the rank of the gauge group, and the dimensions related to this number n can also be given in terms of what is known as the dimension of invariant polynomial of the group. So it's some group theory property that can be determined from the gauge group. Now, for the n equal to 4 SCFTs I'm going to consider here, the model space is turned out to be freely generated by these basic invariants. So the idea is that we now understand the structure of the model space of the n equal to 4 theory, and our compactification preserve more than 8 supercharges. So we expect the model space now to change after this issue that some direction will be lifted when we do this with compactification. In particularly, since we recall that you have this, compactification recall that you have this for this periodicity condition. In particular, this periodicity condition generally causes if any operator is not invariant under the symmetry is going to be projected out. The reason is that once you compactify, you need to expand into loser Klein mode, and the zero mode in general is not going to obey this relation if there is an non-trivial transformation. So the zero mode is going to be projected out. And the only thing you're going to end up with the KK mode, which are going to be massive. So your only massless operators are going to be whatever is invariant under the symmetry. So in general, you expect from the UN that only from the original theory that spanned the model space, only the ones that are invariant under the symmetry are going to survive. So since you start with some freely generated space given by this UN, and since you expect that the model space not to change up to the fact that some of these UN are going to be projected out, the model space you're going to end up with is just going to be the subspace spanned by the UN that are invariant under the symmetry. So what you basically need to determine to understand the model space of the lower dimensional theory is understand which one of these UN operators are invariant under the action of the symmetry. So again, for that we need to understand how the symmetry acts on this UN operator. Now, like in the previous case, the sigma and tau transformation are not going to do anything because they act trivial on the local operator. And as duality also turned out not to act in any way on the UN operator. Actually, the only thing that acts on trivial on the UN operator in this action we consider is actually the R symmetry transformation that we need to combine with the action to preserve supersymmetry. Under this R symmetry action, the UN are then going to transform in this way. They're going to provide some phase, which depend on the dimension and also on K, the precise subgroup of the SU4 symmetry you're using. So in general, once you understand it, you can basically determine which sort of the UN are invariant, which are non-invariant, and you can use it to understand the structure of the module space of the theory you have in 3 dimensions. Now, when you do this in general, you do for many cases. In many cases, you usually find module spaces that seem to be consistent with known n equal to 6 SCFTs, notably of type ABJ or type ABJ. And that plus some string theory consideration actually leads to conjecture that these theories will most likely relate to these cases. So in most cases, you end up just with known, and you appear to end up just with known 3D n equal to 6 SCFTs. However, there are some cases where you happen to have something that doesn't appear to be of this type. And not surprisingly, this happens when the theory is an exceptional. In the next little bit of time I have, I will try to illustrate some examples. So the specific example I'm going to consider is going to be the case where your gauge algebra is E7. The reason that makes this choice a bit appealing to discuss is that E7 actually has a Z2 one-form symmetry, which is exactly the same one-form symmetry as SU2. In fact, everything I discussed for SU2 just goes exactly in the same way also for E7, but just replacing SU2 with E7. They're exactly 3 global variants with exactly the same properties, and they're written in exactly the same way under the SL2Z in sigma tau transformation. So all the spectrum of invertible and non-invertible symmetries I mentioned are also the same thing for this case. In particular, you have a Z2 symmetry. If you take it, there are 2 cases. One of them is it's equal to y. In this case, you have a Z2 symmetry, which again is becoming invertible symmetry. So we can actually think about a Z2 symmetry of a specific model, specific global variant, which in analogy with SU2 case, I'm going to call it E7 mod G2 minus. Of course, in a non-invertible case, it will become an analytic 2 symmetry. Similarly, if you look at if you take the case of the time and means is distributed to infinity, you now have Z3 symmetry. Well, it's really, of course, the Z3 part in this case, it's only just the part that acts invertibly. It actually is a non-invertible symmetry. There is actually no variant which is invertible, so it really is an analytic 3 symmetry. We can now consider compactification, physical compactification with these symmetries, and you can analyze the module space. The module space is pretty consistent with it being some quotient of a discrete of some flat space with some discrete groups. It turned out to be exceptional complex reflection groups. The important property is that it's actually yes.
So how do you compute these 8 dimensions here?
Oh, basically, what the basic strategy there are 2 ways you can do that. One a bit more exact and one a bit more. The simplest one is to just look at the invariant polynomials you have, these UN operators, and understand which one of them are the main invariant under the action of the group. So you project out all the things that are invariant, and then you end up with some collection of the UN operators that are the invariant operators. They should span the moduli space that you have after the reduction. So you again expect it to be some orbifold of the group because the original one is an orbifold. So the other one you have after to be still an orbifold. It should also be freely generated. And it's known that if you have an orbifold that's freely generated, the group that acts as some complex reflection. So you can use, in many cases, the dimension of the invariant is enough to just understand what this complex reflection should be. And then the structure of the dimension of the space should be determined by the fact that the complex reflection will actually act on it in a natural way.
What is the order of the group? Is it the label?
Oh, no, the labels, the order of the group is not actually, the label is there is some classification of these groups in Bachatera and Todd, and the label is like the index number in that classification.
I see.
The order of the group is not, you can read it, you can find it up on the internet or just in references.
I see. And so is it related to the Weil group of E7?
It is related. Both of these groups are subgroup of the Weil group of E7. And you can actually derive this relation a bit more explicitly by analyzing what sort of subgroup of E7 is consistent with this action of this compactification.
I see.
That's another way you can derive this.
And the subgroup, the order of the subgroup is 2 and 3 respectively?
Is what? It's
a normal subgroup of order 2 and 3?
Well, the details, I don't know. There are subgroups of the, I'm not sure whether they are normal or not. And the order is something I'm not sure about. We didn't actually look into this.
Okay.
Can I ask a question, Gabi?
Yeah, sure.
I'm a little confused about the sort of reduction in the dimension of the moduli space. You're essentially gauging a discrete symmetry. So I understand that you're going to project out the invariants which are not in neutral under it. But for instance, I don't know, say some invariant of E7 was odd under that Z2, then the square of that would be a new invariant even under it.
Yeah.
In other words, I would expect the dimensionality of the moduli space to be preserved.
Yeah, well, the problem is that this is essentially because the physical multiplication is not equivalent to gauging. You are not actually gauging the symmetry. What happens with physical quantification is whatever or not the operators are not inverted, the symmetry is basically acquire a mass in lower dimensions.
I see.
And that's why the dimensional is actually reduced. You actually have less operators to give F to compare to original.
Okay.
Gauging will produce a different moduli space, which in general will not be freely generated because you're going to start having relations between the different operators.
Okay. Okay, thanks.
No problem.
One more question. Did you compute the Hilbert series for those two spaces?
Well, no, we did not. It's a freely generated moduli space. It's naively suspected should be able to compute the. There's some slight difference depending on what precisely do you want. Do you want the X branch, which is some subspace of that, or do you want the actual full moduli space? But the full moduli space expected should be easy because it's just a freely generated space, right? The invariant of dimension you know. But if you're looking at the subspace, it's going to be a bit more complicated.
So you're saying it's freely generated. One of them related to E7, the other to E6.
Well, this one is freely generated by two invariants. I can give it a dimension if you want, and this one is generated by three invariants. Again, I can give it a dimension if you're interested.
How can it be freely generated if it's of dimension 8?
Oh,
the number of generators should be equal to the dimension.
Yeah, but the thing is that, okay, it's a bit, there is an SO, this theory, well, it's really, you can really think about it. It's acting actually like diagonally on C4. So you have two C4s here, and take diagonally on both of them. So you only have two trivial, and then it's actually transfer. This has to do with the fact that theory is an SO6 global R symmetry, which is our default commute with. So it really is two collection of C4 that transform under it. And similarly also here, it's just it's C4 to the cube, and the collection of C4 is what actually transfer, and then transform until D26.
I see. Okay. Yeah. Okay, thank you.
Okay. All right, so as I was trying to say, so we can understand the moduli spaces, and in particular, there's actually no n equal to 6 SCT that has these moduli spaces. And this only suggests this n equal to 6 SCT is actually new n equal to 6 SCFTs. One interesting aspect particularly is that this one, as I mentioned, you can only access it with, at least in this class of construction, you can only access it by doing this twist compactification of E7. In particular, in this case, as I mentioned, there is no variant which is invertible. So in some sense, this model is something that you would not be able to get if you would not perform twist compactification just by invertible symmetry. In contrary, this one you can in principle get from an invertible symmetry, the one from this model. This is also interesting. You can actually see that these non-invertible symmetries tend to be essentially if you want to get new models. All right, so I think I will conclude. So talking about how recently there has been a renewed interest in novel types of symmetries. Now, for the most, we'll mostly discuss this case of non-invertible symmetries. You can think of as symmetries that actually do not form a group. I've talked about how these can appear in 4 dimensions. What particular way when they appear is some invariance and aggregation of one-set symmetries. In particular, I noticed they appear even in n equal to 4 subdomains, theories are just pretty familiar with, and can actually be studied quite systematically. You actually categorize them and understand how many of them they have precisely do in the method I described. Also, I noticed you can actually perform twist compactification by these symmetries. This can be used to realize new theories. In the case of the specific n equal to 4 subdomains, they can be used to realize new n equal to 6 SCFTs. So there are several other directions you might consider. One is it might be interested in the other application of these non-invertible symmetries. Specifically, can they be used to constrain RG flows of n equal to 4 subdomains in some way? Another interesting idea is possible to generalize to n equal to 2 SCFTs that share similar geometric construction with the n equal to 4 subdomains. Specifically, what I have in mind here is that we can think of n equal to 4 subdomains as being given by the compactification to 0 theory on a torus. And this non-invertible symmetry can sometimes realize the various properties of this model, particularly the fact that the toric develop additional isometries and specific value of the complex structure concept. Naively, we know that this construction can be generalized more to many other n equal to 2 SCFTs by either by changing the Riemann surface or by changing the six-dimensional the 60 theory. It can be interesting if these non-invertible symmetries might be some phenomena that is more general and also in these models. Better interesting is to try to understand better this restriction on twisted compactifications. I've mentioned that it's not just everything goes. In general, when you have a cycle, you are restricted by the homotopy group relations. For normal symmetries, we usually just say that the space of this complication is given by some homomorphism from the fundamental group to your gauge group, to your symmetry group. Now, it might be interesting to understand what is the analog statement for in the more general case, where you don't have just zero form symmetry, but you have this more general case that include higher form symmetries and also potentially non-invertible symmetries. Understand if there's some statement similar to that in this case. Finally, it will be interesting if you can also see more about the result n equal to 6 SCFTs. Okay, so thank you. That's basically it.
All right, let's thank Gabi. And do we have more questions?
I have a question. I thought there was like a Z2 subgroup of the SU4R symmetry, which could be which preserved which combined with the Z2 and the S duality group preserved n equals 4 supersymmetry.
Yes, that exists.
So if you do a twisted compactification with that, do you get n equals 8, new n equals 8 theories in 3D, or?
No, it doesn't seem that way, because it usually acts like, for example, for SU2, it is like a charge conjugation. So you just naively end up with n equal to 8 theories of O or USP groups, which are of course known.
I see. Okay, thanks.
Hi, Gabi. So I have a question.
Hey, yes.
So we kind of know that there is a classification for the 3D n equals to 6 SCFTs, the Lagrangian series. But I just wonder whether there's any relation between your new series and the known ABJM type series.
Yeah, so as I briefly mentioned, again, the main thing we know about these theories is the model spaces. And we have some, you can also try to use this string theory to build some form of, to try to use the string theory construction to try to link the two theories, and kind of look like in the case where you have classical groups. So if you start with an n equal to 4 theory based on SU, USP, or SO type gauge group, then the theory that you're going to end up seems to be just ABJM or ABJ type. You can usually find some ABJM or ABJ type that you can presumably relate to. The interesting thing is in the exceptional theories. This is where you usually get model spaces that are not of the type that you will get from ABJM or ABJ type.
Yeah. So you are not. So you don't know any relation between this series and the ABJM type thing.
Well, for the exceptional group, there appear to be new theories. For a classical group, I suspect that there is some relations, and there is some mapping. We have some proposal conjecture of what the mapping should be in the paper. For the case where you have the classical groups.
I see, thanks.
No problem.
More questions? Okay, so if we have no questions right now, then let's thank Gabi again. And I was recording.